The ultra-wide bandgap semiconductor beta gallium oxide has shown its great potential in high voltage and low loss power devices because of its large bandgap, wide range of N-type doping, and thus the outstanding overall performance, like shown in the left figure. However, the lack of P-type doping makes it challenging to fabricate high-performance gallium oxide devices. So researchers are seeking for suitable P-type materials to form high-quality heterojunction with gallium oxide. Nickel oxide is one of the possible choices. In our process, we propose to reproduce the heterostructure like shown in the right figure A by deposit nickel on the gallium oxide, followed by thermal annealing to oxidize nickel to nickel oxide. However, due to the characteristics of nickel of being easily to diffusion at high temperature and the instability of the oxidization process, certain characterization methods should be employed on the substrate and the heterojunction to ensure the achievement of high-performance devices.
The first technique we would like to use is the atomic force microscope, which is used to mapping surface morphology and roughness. What it does is to scan a sharp probe across the sample surface to measure topography at the nanoscale. It does not require conductive coatings, which is preferred for our oxide materials. And also it provides a 3D surface mapping. There are three key measurements for our samples. The first one is the surface roughness. This is critical for the quality of the subsequent layers and the metal contacts. We will measure RMS roughness. The second one is the grain size and its distributions. How uniform is the polycrystalline nickel oxide films? The third one is the interface quality. We need to identify peaks, cracks, or contaminants at the surface that could affect device performance. The device we will be used is a Berkeley PT scanning probe microscope, which is settled in the room 2153.
So the second characterization we want to perform is the scanning electron microscopy, or SEM. SEM is a powerful tool that works by scanning a focused electron beam across the surface of our sample. It generates high-resolution 3D-like images that reveal surface topography. And second, it can provide elemental analysis to confirm chemical composition and distribution. We've chosen SEM because it is the ideal technique to directly see and measure the critical features of our samples. Specifically, we will be using it to confirm whether the P nickel oxide film achieves the target thickness to ensure consistent electrical properties. Also, we will examine the surface morphology to verify that the P nickel oxide strips are continuous and uniform. Second, utilize the SEM-based focused ion beam module to mill and lift out site-specific cross-sections. This process is essential for preparing electron transparency samples for subsequent TEM analysis.
After the sample has been prepared, we would test it through TEM to give us the information about the atomic scale structure and its crystallography. About what it does, it transmits a high-energy electron beam through an ultra-thin sample, usually in nanoscale. And also, it provides the highest resolution imaging down to the atomic level. It also has three key measurements for our nickel oxide and gallium oxide sample. First one, it tells us the crystal structure. So we can confirm the crystal phases of both nickel oxide and gallium oxide. Second one is the interface atomic structure. It resolved the atomic arrangement at the heterojunction, so we know is it abrupt, are there any defects or dislocations. The third one is that we can have the selected area electron diffraction, which is usually referred to the SAED. So we can analyze the crystallinity and orientation relationship between the nickel oxide film and the gallium oxide substrate. The equipment we would like to use is the TM located in room 2212.